Welcome everyone. This is the afternoon session. I hope you enjoyed the previous sessions of the two panels that we had, and we also had some break between all the presentations. So my name is Antonia Zemanaki, and together with my colleague George Jenkinson, who is a doctoral researcher at the Bristol Robotics Lab, we will be presenting and chairing the afternoon session. So I'm a lecturer in robotics, and I will be presenting later. For now, we have, to kick off the session, we have Dr. Shane Windsor. Welcome, Shane. So over to you. Please do share your screen with us, and you can take it away. Oh, let me introduce you quickly. I'm sorry. So Dr. Shane Windsor is a senior lecturer in aerospace engineering at the University of Bristol. His research is multidisciplinary with a focus on bio-inspired aerial robotics. He is currently leading the £3 million UKRI Trustworthy Autonomous Systems Node in Functionality, the project which he is going to be telling you more about today.
Great, thanks very much. Good afternoon, everyone. So my name's Shane Windsor, and I'm going to be telling you today about the project which we've just started up, looking at developing trustworthy, adaptive, autonomous systems. Now, this is part of a much larger national program, which is the UKRI Trustworthy Autonomous Systems Program. This is a very large program running over the next 3.5 years, funded from the Strategic Priorities Fund. It's a £33 million program across the UK, and it's being led by the EPSRC with support from all the other research councils. And what I'm going to tell you about today is the node in functionality, which is the part of the project that I'm the primary investigator for. But I thought I'd just start out with just give you a little bit of context for the Trustworthy Autonomous Systems program for those of you who might not have heard of it before. So as I said, this project or program started up mid-2020, and the structure of it is a hub with 6 nodes, of which I'm going to be telling you more about the functionality node today. And the overall objective for the program as a whole is to build a community around trustworthy autonomous systems and invest in fundamental research to address all the things that go around autonomous systems in turn that are needed to be in place before we see them operating really commonly in the everyday real-world environments, addressing questions such as the technical side, but also the social side, the ethical side, resilience, security, governance and regulation, all these aspects that go around autonomous systems when they're in application in the real world. So that program is looking at the complete picture of autonomous systems and what needs to sit around them and how we need to work with them to develop everything that needs to get these in place. And the idea of the program is to be a focal point in the UK for advocacy and engagement around autonomous systems. Now, the hub is the center of this activity. Its job is to coordinate the fundamental research which is happening in the 6 nodes and to build a community. It's the interface for advocacy as well as having funds which it can use to focus research. And then we have the nodes. So we have nodes in verifiability, trust, security, resilience, governance and regulation, and functionality. So now I'm going to tell you more about the node in functionality that is being hosted at the Bristol Robotics Lab. And I'd like to introduce my team of co-Is. So this is a multidisciplinary project. So we have John Downer from sociology, looking at risk and resilience. Kirsten Eder from computer science, looking at verification and validation. Jonathan Ives from empirical bioethics and medicine, looking at aspects of ethics. Dr. Speen Howard, looking at swarm robotics. Jonathan Rossiter from BRL looking at soft robotics, and myself with a focus on bio-inspired unmanned air vehicles in particular. So I should say all of this work is going to be based at the Bristol Robotics Lab. We started off in November, so we're still to get our feet under the desks physically in there for some of the aspects of the work, but the project's been underway remote working since November. And this project has 11 project partners, as you can see here. These are companies that we're working with an interest in trustworthy autonomous systems, and each of them has different aspects which they bring to the project, from understanding the regulatory environment to developers of technology to regulators as well. So the focus of our node is on evolving functionality. And what I mean by evolving functionality, basically I mean that we're defining functionality as what a system is meant to do, what it does do, and what it could do. And this changes over time. Traditionally, we see the change in functionality for a system changing slowly. Each time we release a new generation of system, it has some different functionality to it. However, we're starting to see the emergence of autonomous systems that can adapt and evolve their functionality in operation. So through learning or other adaptation mechanisms, they can actually change some of the way that they work, some of their functionality in operation. And this can make them more flexible, more adaptive, more suited to deal with everyday complex environments. However, this raises a number of challenges around how to specify these systems, how to design them, how to verify and validate them, and regulate them. Because all of our existing methods generally make the assumption that as soon as the system leaves the manufacturer or the factory and goes out into operation, that it's not changing in terms of its fundamental functionality and the way it works. However, if we give the systems the ability to adapt and evolve to make them more suited to complex real-world environments, do we need to change the processes that we're using around these systems in light of this, and in light of this ability, giving them this ability to adapt and evolve? So the objectives for the node are to investigate this question of how, when we give an autonomous system the ability to adapt, what processes we need to use, or how suitable our current processes are for dealing with this. And the goal is to design a set of to develop a trustworthiness framework designed for trustworthiness, where we look at the aspects of specification and trust and verification and validation and regulation together in a holistic way, with the focusing on adaptive autonomous systems, and create best practice guidance when considering these types of systems. So how are we going to go about this? Well, the node has 7 work packages, and we're focusing on 3 different types of technology, all of which have fundamentally different ways in which they adapt. And I'm going to introduce these in a little bit more detail as we go through, but we're looking at swarm robotics, soft robotics, and unmanned air vehicles as the technologies where we're developing them with adaptive abilities. And around this, we're looking at the specification and monitoring of these systems, the regulation of these systems, the ethics and trust considerations with these systems, and questions about how to verify these systems. And the way we're doing this is to actually go through development cycles, a number of different development cycles during the course of the 3 years. And in each development cycle, we'll be looking at applying the guidance and techniques in terms of regulation, verifications, and specification to the design process used for developing an autonomous system with adaptive technologies. But while we're developing these technologies, we'll be feeding back how those guidelines and techniques have helped the design process and what things could be improved in the design process to make better consideration of the ethics, the verification, and other aspects, and to bring them right into the beginning of the design cycle. So we're considering all of those aspects right from the beginning, even at very low technology readiness levels. And then the idea is to iterate through this, where we develop new guidelines and techniques and methods, and then apply these through the design process, and then feed this back to then influence the next design cycle. So the idea is to have everyone physically based in the Bristol Robotics Lab working closely together on these aspects, and bring in our project partners into this design process and evaluation process as we go through. So the first adaptive technology we're looking at is swarm robotics, and this is the work of Sabine Howard. Now, the particular use case we're looking at is the idea of a pop-up cloakroom. So the idea is there's lots of robots that work independently in a swarm, which can be put into an unstructured environment and operate a cloakroom. So you come up to one of these robots or a particular location, you give it your jacket, and then it will go away and deposit it and store it. And the idea with the swarms is that you can do this without needing dedicated infrastructure. It can be low cost, it can be flexible. And what we're really interested in looking at in this design, in this particular use case, is how to design this system in such a way that we consider the aspects of its performance as well as its trustworthiness, its ability to be verified, its ability to be regulated right from the beginning. And in particular, looking at how, if we change the number of robots or the complexity of the individual robots, this influences this ability. And I should just jump back and say, for these robots, the adaptive aspect actually comes through the emergent behavior and the interaction of the individual robots in the swarm. So we don't necessarily need the individual robot to adapt, but because of the interaction between an individual robot with its environment and with the other robots, you get adaptive behaviors occurring. If you'd like to find out more, I think Sabine's spoken earlier today, and the link to her website is up there. Second adaptive technology we're looking at is soft robotics. And this is the work of Jonathan Rossiter. Now, for those who aren't familiar, soft robotics is the idea that you can make robots out of soft, compliant materials, not just rigid plastics and metals, but actually you can use smart materials with embedded actuators and sensors and power sources in clever, novel ways. And the adaptation in this type of system can come through the material properties of the materials that you actually use to build the robot. So this is a fundamentally different way of adapting, and it's based on the structure and materials used in the robot and the way they're all coupled together. And in this particular project, we're going to be, in the nodes, going to be looking at the development of standards for trustworthy soft robotics. This is a very new and low TRL level exercise on the whole with most soft robots. So there's a real need for thinking about the next step as these advance in technology readiness level for what sort of standards might need to be applicable to these. What might they look like? How would you go about designing it when you've got such varied types of mechanics and materials involved? And so Jonathan's design will be leading the development of a number of different soft robotics for applications such as gripping, locomotion, surgical manipulation. And if you'd like to find out more, there's lots of information there on his website. The third adaptive technology we're looking at is unmanned air vehicles. And here the adaptation is actually happening through machine learning algorithms, which are being embedded or being made part of the flight control system for the unmanned air vehicles. And this is part of the work package that I'll be leading. So here we're looking at the application of machine learning for flight control. And the particular case studies we're looking at is the use of multi-rotors in urban environments, and we're going to be testing this out with scaled down quadcopters flying around in the Bristol Robotics flight arena, and also looking at morphing wing unmanned air vehicles, which we're developing which have distributed sensors in the wings of the vehicles. And this is inspired by what we see in birds and insects, where they have lots of sensors distributed all across their wing, which pick up on airflow information and forces and acting on the wing. And here we're looking at how we might incorporate different machine learning aspects into the flight control system. From hybrid systems, where just small components of the flight control are based on machine learning, to fully machine learn-based control systems, where we are developing potentially reinforcement learning-based controllers or end-to-end controllers, where we have the complete spectrum from hybrid systems, which are mostly conventional, all the way through to fully machine learned control systems. And here we're looking at how, when we start bringing machine learning into these type of systems, how this influences the design process, and then the verification, regulation, and ethical aspects that arise from this. So I've talked about the technologies, and the next aspect I want to talk about is actually these technologies are being used as use cases and study examples for actually what do we need to do around these type of adaptive systems to make them usable in the real world in terms of all the other aspects that are needed for a system, such as specification. So if you've got an adaptive system, how do you specify it? How do you inherently want to give it the scope to move beyond the kind of conditions that it's made for as it's being in the factory? But how do you specify the limits on that system? And how does the other aspects, such as regulatory considerations, verification considerations, change the way you might specify the system? Next aspect we're looking at, this has been led by Jonathan Ives, is the idea of trust for an adaptive system. What does it take for a technology to be trustworthy? Why do people trust particular technologies? And what can developers do to facilitate trust, to illustrate trustworthiness? And what changes if we give the system the ability to adapt and evolve actually in operation? We learn to trust by experiencing and interacting with systems. If one day they can suddenly potentially change and operate in a different way from we expect, does that change the way we learn to trust them? And for this part of the research, we're using an embedded researcher model where we're actually having ethicists who are going to be working alongside those developing the technologies to look at how the developers think about trust, how users think about trust, and how manufacturers think about trust as well, to understand the different aspects of trust and how this is influenced by the adaptive nature of the systems involved. Related to this, we've got John Downer leading the work package looking at regulation, asking questions about how do adaptive systems influence the regulatory requirements. And John's going to be using 3 axes as such to investigate this, looking at how, if the purpose of the same robot changes, how this changes the regulatory requirements. For example, the same robot might be used for assisting in surgery or stacking boxes in a warehouse. How does that change the regulatory requirements for the same system? Similarly, if we're starting to use different methods of design from a traditional code base versus machine learning, for instance, how does this change the aspects of regulation? And then if the same system is operating in a different environment, such as public airspace versus a private warehouse, how again does this influence the regulatory requirements? And in particular, how are these requirements shaped by, well, the regulatory requirements shaped by giving the system the ability to adapt in operation? And how do you verify these systems? This is the question that Kirsten Eder will be looking at. When we're thinking of these systems, how do we specify the requirements for them in a way that means that they can be verified? How does it change the design principles we need to use for verification when we're considering adaptive systems? And how do we need to demonstrate for autonomous systems with evolving functionality that they can be considered trustworthy and in a way that is suitable for regulators and for end users? And as part of this, we need to understand what can be verified at design time, which is when we traditionally run verification, and what needs to be left or considered during runtime. And does this actually change how we design the system and change the way we consider performance once we're thinking about verification as a first-class design goal? So, as I said, this project is currently underway. We're running for another 3 years, and we're really interested in talking to people or parties or companies who are interested in this question of, when you have an autonomous system with adaptive abilities, how does that change how we consider these systems? How does it change the way we trust them, the way we design them, the way we regulate them and verify them? What is it that we can take from our current ways of doing things and apply to adaptive systems? And what aspects do we need to change in our processes to account for and make them better suited for adaptive systems, and allowing us to unlock the potential of adaptive and learning-based systems in the real world? If you'd like to find out more, please have a look at our website, or you can email me as well. Thank you very much, and I'm happy to take questions.
Thank you very much, Shane. Thank you. That was quite a fascinating talk, and so much that is being planned and done in these concepts. So we do have a couple of questions, but please continue to post your questions in the comments. We do have a few minutes for them to answer them. So the first question I'd like to ask here is, how will the work that you've been doing in your node and that you will be doing, how will it interact with the rest of the TAS program?
Yeah, so that's a really interesting aspect that we're currently developing at the moment. So we've got the 6 nodes, which all have their own focus areas, but a lot of those areas overlap in a lot of interesting ways. So at the moment, there's a lot of interactions between the different nodes looking at the complementary research that's taking place. And there's, through the hub, a whole lot of mechanisms that are in place to try and make the most of this large community which is being built. And in the coming year, there's a number of different funding opportunities that the hub is running that might be of interest to this community. There's pump priming funds which are available to look at the areas that aren't being covered, or the collaborative possibilities from the research across all these different areas. So if you're interested in getting involved with the TAS program, I recommend looking at the TAS hub. There's a lot of funding opportunities coming out over the next few years, and they're building up a community, running a number of workshops and activities all the time around trustworthy autonomous systems.
Thank you. That led, I think, partly to my next question, which was, how do people get involved? And I know in your last slide, you actually have the website there. So is it through workshops? Should they contact the lead or for each part? How would you recommend they go about it?
Yeah, so it depends. If there's a particular aspect, say, such as security, that you're interested in, then there's a node in security, and they've got contact details on their website there. If you're interested in being involved in the program as a whole and getting an overview of kind of trustworthy autonomous systems and the events that are happening, I'd suggest talking to the hub. I should have put their website up here, but if you just search TAS, the Trustworthy Autonomous Systems Hub, they've got a great website and lots of channels and newsletters that you can sign up for there to see the activities that are going to be happening over the next 3 years, such as workshops, conferences, and also the funding calls as well.
Thank you. I believe the website is tas.ac.uk. Is that right?
Yeah, it's the one. Yeah.
Okay, I can post it in the comments as well for you. Any other questions? We do have one or a couple of minutes. Or Shane, if there's anything else that you would like to add.
Oh, I think I covered everything I'd like to today.
Okay, then. Okay, so we don't seem to have any more comments or questions for now. So with that, then I will thank you for your talk and for the work that you do. And I wish you a good afternoon and to enjoy the rest of the talk.
Great. Thanks very much.
So for our viewers, we have a couple of minutes more now until our next presentation. So I'm going to wait for this until 2:30 sharp before I start it, to make sure that people joining at 2:30 exactly do not actually miss out. So that's a good opportunity maybe for a little bit of a comfort break after a couple of minutes. Hello again. So this session now, we're going to continue with our next talk. And the talk is by Dr. Zhenyu Lu. Unfortunately, Zhenyu was not able to attend right now, but he has sent us a recorded presentation, which I will play for you. So to introduce the speaker, so Dr. Zhenyu Lu is a postdoctoral researcher at the University of the West of England and the Bristol Robotics Lab, who works on robot teleoperation. His presentation today will introduce their work on a dual-arm cooperative teleoperation using robotics, as well as human skill learning and generalization for dual-arm manipulation. So I'm going to share now the presentation and you can watch it here.
I'm Zhenyu Lu. I'm a postdoctoral research associate of BIL. I would like to present my slide about robotic cooperative teleoperation and skill learning. As we know, teleoperation is a technology that one operator handles the facility to control a foreign robot to complete the task through long-distance communication. Compared with single robot teleoperation, the multi-robot case needs a multi-operator to control multiple robots and will cause research problems such as about the robot interaction, trajectories planning of the multi-robots, and control stability problems for the complex networks environment. Here we mainly consider the case with two robots to complete a human-like cooperative action. Inspired by human beings, that the two hands are divided into the dominant hand and the non-dominant hands. The dominant hand is used for positioning and leading actions, and the non-dominant one is to assist the dominant. So we divide the two robots into the dominant robot and the non-dominant robot. The dominant robot is to track human hands motions, and the non-dominant one will react like the non-dominant hands to help the dominant robot. A controller for the robot and the manipulator in the master side are designed differently. First, for the dominant robot, we designed a position tracking controller with a robust term. For the non-dominant robot, the controller is designed to realize different purposes for different conditions. If the relative distance to the dominant robot is too large, the non-dominant one will first minimize the relative motions and then follow the corresponding leading hand. Here are the exact expression of the different controllers for switching or for the non-dominant robot. And in the leader side, the controller is designed to track the motions of the robot by using PD control. After building the model of the object control force, we complete the experiment of the picking and placing a ball by teleoperation. Teleoperation is also a way for learning from demonstration technology, which is a practice for enabling robots to autonomously perform new tasks. But sometimes the demonstrations are facing the challenges such as the occlusion, rapid object movements, and have some mirroring sensor noise, which makes the learning results failed. What we thought is to add some special constraints to the skill learning process. DMP is a common way to skill learning, and its expressions is very simple. Just has one damping and one stiffness factor and a force nonlinear function Fs. After segmenting the demonstrations into primitive skills and making alignments for the segments, the skill will be learned and generalized to new cases by changing the starts, ends, and scaling factors and applied to the new tasks. What we do is adding the new term to the original DMP expressions, and we use the barrier Lyapunov function to generate the additional term to enable the skills to satisfy the constraints. For the redundant robotic arm cooperative manipulation, we present the following solution by using the zero-space method to optimize the joints.
I believe this was the end of Zhenyu's recorded presentation. So since he cannot be here to answer any questions, I will go back perhaps to his initial slide at the beginning of his presentation, which you can find his email and contact him directly. So moving on to the next talk now. The next talk is also a recorded presentation. It is by Dr. Hema Phillimore. Unfortunately, she couldn't be here at this time. So Dr. Hema Phillimore is a lecturer in robotics at the Department of Engineering Mathematics of the University of Bristol and a member of the Soft Robotics Lab and the Bristol Robotics Laboratory. In her presentation, she discusses soft robots that connect isolated people. I'm going to share now the presentation.
Co-creating soft robot avatars to expand access to creative spaces. An ongoing research project by Hema Phillimore from the University of Bristol and Adrian Hart from Neon Dance. Hello, I'm Hema Phillimore. I'm a researcher in soft and biohybrid robots at University of Bristol, I'm going to be talking about an industry-led project that I'm currently working on. The project is in its early stages, but I wanted to share this work as an example of an emerging use of soft robotics within industry. The work fits within the emerging use of robotics to augment and empower humans. In particular, we were inspired by recent work using robots to give people access to spaces they could not physically occupy. This includes work by researchers at the Bristol Robotics Lab on using double telepresence robots to engage visitors to access the Hastings Contemporary Art Gallery in the UK during the national lockdown. Robots are increasingly being used as companions and helpers in care homes for older people. And the Dawn Verbita Cafe opened in Tokyo, Japan in 2019. The hospitality staff were robots, teleoperated remotely by people with severe physical paralysis, providing access to financial, social, and professional independence for the human operators. The goal of my current project with Neon Dance is to develop soft robot avatars through which humans can access creative spaces, such as performances and art galleries, in a new and interactive way. Our project aims to empower and connect humans through automation, as opposed to invalidating them. In order to develop something that is truly user-centered, we are exploring ways to democratize technology by bringing end users from non-robotics backgrounds in as active participants in robot co-development and designing interfaces to facilitate this within familiar and public spaces. The overall goal of this work is to develop a kit of robot avatars which will be used to connect isolated people with cultural spaces. By teleoperating robot avatars from their homes, initially via video call, people experiencing isolation and loneliness will be given the capability to utilize embodied agents as a means to participate in arts and cultural events. To get to this point, we are working with a group of socially isolated older and younger people to co-design miniature soft robots through a series of workshops. The first milestone of this work, which is scheduled for the end of this year, will be to use the co-developed agents as avatars that will be teleoperated by their co-creators, the workshop participants, in order to access an art installation devised by Neon Dance. This will be presented at several venues throughout the UK and internationally. Within the installation, a group of miniature robots, some teleoperated, some operating autonomously, will interact with a live in-person audience. The teleoperated robot avatars will facilitate interaction between the audience at home and the in-person audience, the other robots and other at-home audience members via their robot avatars. Our intention is to provide not a filtered version of being there in person, but instead a different version of the same reality, a remote augmentation of the operator's body that feels meaningful and connected. My collaborator, Adrian Hart, will now explain more about the vision for how the robots will be used from the perspective of our partner artists and venues.
Hi everyone, my name is Adrienne Hart and I'm the Artistic Director of Neon Dance. For the past 16 years, I've been creating dance works that explore technology and design with the body as a central tenet. Collaboration is at the heart of my practice, and I bring together artists, musicians, technologists, scientists and academics to create collectively what we could not create alone. In 2020, I started working with the roboticist Hema Phillimore at University of Bristol's Robotics Lab and artist Akabik to explore social connectivity and collaboration using bio-inspired robotics. The work is designed to unravel the origins of loneliness and explores the idea loneliness stems from the interaction of the individual with the social realm, so that it's not just mental, but also physical, sensorial, and material. Titled Prehension Blooms, our aim is to create a totally unique interactive performance experience with audiences free to roam, encountering 3 highly skilled dancers and a beguiling, playful robot community. By moving, sitting, lying down, and congregating, the audience will influence all aspects of the performance, creating a genuinely interactive experience. There will also be up to 6 teleoperated robots, which enable remote audiences to traverse the environment, interacting with physical audiences, fellow robots, and performers. Throughout the making process, we have actively worked with members of the public, creating a set of easy-to-operate building block devices to demystify the work on robotics being embedded into this production. In a series of workshops beginning in June, here in the UK, there will be the opportunity to play and experiment with these building blocks and co-author the design of our miniature robot community. The general robot design ideas are coming from social insects and cooperative collective behaviours. The idea for the robots is to have these Telson-like structures of different modular parts, which can move both in unison and separately. We're also exploring the idea that they can be reactive to touch, light, and proximity, changing movements and shape depending on their surroundings. So one possible scenario is that an audience member or performer could come up to one of the robots and touch its body. Perhaps the creature grows or shrinks in response, or even wraps itself around their arm.
In this work, we are looking at how soft robotics principles and techniques can enhance the user experience of a telepresence robot. For example, we are exploiting the superior capabilities of soft robotic actuators for organic biomimetic motion and compliant tactile interaction to build robots that we intend to be safe and inviting to interact with. We found it a challenge to predict what type of robot morphology or movement audience members would want to use to access a creative space or performance remotely. So we produced a set of building block devices to enable us to workshop different ideas with members of the public. We generated a set of bending tentacle-like components made from 3D printed TPU rubber. These were actuated using a simple setup of either 1 or 2 antagonist pairs of artificial muscles. Like in the musculoskeletal systems within our bodies, when an agonist artificial muscle contracts, it causes the robot tentacle to bend. When an antagonist muscle, the opposite muscle in the pair, contracts, the robot bends the opposite way, and the antagonist muscle is extended to its original length. The artificial muscle actuators are shape memory alloy, or SMA, wires, which are made from a nickel-titanium alloy known as nitinol. They can be made to contract by heating and lend themselves well to miniaturized and mobile systems due to a minimal requirement for driving electronics and other hardware. SMAs can be plastically deformed at relatively low temperatures in what is known as the martensite phase. Upon exposure to high temperature, approximately 250 degrees C, for example, dual heating by passing electrical current through the wire, the SMA will enter its austenite phase and recover its original shape. An SMA wire, for example, can be extended by applying tension to the wire when in its martensite phase, but when heated to its austenite phase, it will apply a force acting in the opposite direction as it returns to its original shape. A common configuration is therefore to arrange the wires as an agonist-antagonist pair as shown here. The actuators in the robots are configured as a coiled helix and are arranged in sets of either 1 or 2 antagonist pairs, creating different motion depending on the muscle arrangement. The robot controller used input from a camera and a simple position or motion tracking algorithm to find the position of an object or position of the point of motion with the greatest velocity in the field of view. The robot tentacle followed the position, allowing it to be controlled by a person moving in front of the camera. In some cases, this control was open loop. In others, an additional camera looking at the robot provided feedback of the robot's position, which was used for closed loop control. A wearable breathing sensor developed by Alice Haynes, a PhD student at Bristol Robotics Lab, was also used to control the robots, with the robot moving from side to side in time with a person's breathing. I'll now talk about the first stage co-creation workshops, which took place this month. Members of the public in St Ives in London participated in the design of the robots by controlling simple building block soft robots using the movement of their bodies or everyday objects in the room, and generated ideas for how this could be used to communicate with another human or participate in an activity remotely. The workshop was centered around three main questions. What mode of control makes me feel most connected to this robot? How would I use this robot to interact or connect with another human being? What type of motion and what shape of body would I use to do that, and why? We asked participants to compare three ways of controlling the robot: using motion tracking of their bodies, using position tracking of an everyday object, using a breathing sensor to track inhalation and exhalation. Our goal was to find out what kind of motion participants made when told to control the robot using their bodies, with minimal further instruction. We also wanted to investigate the importance of a physical interface to use as a controller, and whether a passive object could fulfill the role of a joystick or other active controller. The activity allowed us to observe the accessibility of these different types of control and how intuitive they were to use. Participants also experienced controlling actuators with different morphologies and different types of motion. The robot on the left has a more limited range of motion. It simply moves from side to side. Participants quickly learned how to control the robot, interacted with it for a comparatively short period of time, and used simple movements. The robot on the right moves with a greater degrees of freedom. Its motion is slower as a result of the open loop controller used for simplicity in this first iteration. In spite of this, participants engaged with this robot for longer by comparison, and used far more imaginative movements to control its behavior, and even started to work together. Participants were asked to think about how they could use this motion to interact with other humans. This was mostly documented via video recordings, drawings, and notes made by participants during the workshops. Participants were also encouraged to use a compliant sculpture produced by designer Anna Reykjavik to show physical representations of how they imagine the robots moving. We asked the participants to reflect on the experience of controlling the robots in these different ways. We also asked Elaine Check at the School of Education and School of Computer Science at University of Bristol to extract qualitative data from the activity, looking at which activities were useful for communication and promoted interaction between the participants. The outcome of the initial stage workshops are currently being analysed to yield results that will be taken forward to the next round of co-creation sessions with members of the public. In particular, we are looking to address three main topics. We are comparing the positional accuracy that was achieved using the different interfaces for controlling the robots to see if any significant differences in effectiveness can be observed. As part of this, we want to see if everyday objects can act as an accessible, easy-to-understand interface for elderly people, for example, to understand how to control the robots. As participants reported a sense of learning to operate the robot over time, we are also comparing the quantitatively measured accuracy and responsiveness with the perceived accuracy and responsiveness, for the different modes of control. In other words, how accurately the robot followed the movements people made compared to how it felt. A key challenge in teleoperated systems is the lag that can be experienced by end users, and so utilising this perceived accuracy may improve the user experience in the presence of latency. We are also using the image database collected to develop the robot controller and create a state action mapping that is entrained through interaction between user and robot. The goal is to improve the adaptability of the soft under-actuated robots to different movements and users. Lastly, the set of building block actuators is being developed further to allow individual actuators to be connected together by participants to form more complex body shapes. This will allow participants to co-author the robot's overall body shape and movement in the next set of workshops, which will take place at Bristol Beacon later this summer. This modularity is one reason for choosing shape memory alloys to drive the robot actuators, as their driving electronics can be readily miniaturized. I'd like to thank all members of the team involved in this work and all of our funders. Thank you for listening, and do feel welcome to get in touch with any questions about this research project.
Many thanks to Hema for this presentation. In fact, I will put now in the chat their email, so you can have it, and hopefully you can contact her if you have any questions at all. So we are we're a couple of minutes early now. The next talk is actually my talk. I will hand over to George now, who will be moderating the rest of the afternoon session. And George, I believe we have a couple of minutes. We're a bit early, so maybe we should wait a little bit.
Yeah, sure. So we'll, I guess we'll take a break here and we'll come back at just before 3 o'clock with so I can introduce yourself and then you can start and get going.
Yeah.
Or reintroduce yourself, I guess. Okay, we'll see everyone in a couple of minutes. Okay, so I think we're ready to start this next talk. So the next talker is Dr. Antonio Semenaki, who, if you've been on this track any of the day, you will recognize as being the chair usually. So Dr. Antonio Semenaki is a lecturer in robotics at the Department of Mechanical Engineering at the University of Bristol and the Robotics Lab, the Bristol Robotics Lab, and is leading the Dexterous Manipulation and Wearable Robotics Group. Her research includes human and robotic hands and exoskeletons, soft sensing, and haptics, with applications in healthcare and extreme environments such as nuclear and space industry. So I'll hand over to her now.
Thanks very much, George. And I have to say, George is one of my PhD students, so he knows my work quite well. So in the next probably 20 minutes or so, I would like to show you some of the work that we do in my group, and I've titled it Anthropomorphism in Medical Robotics and Beyond, because I'm not going to talk only about healthcare applications, but also about some applications that we have in nuclear industry as well as space technologies. And when I talk about anthropomorphism, I'm not talking about robots looking like human for the sake of looking like human, but I'm talking about a functional anthropomorphism, which is about taking attributes of human behavior, human movement, and then applying it to robotics to actually benefit and have more dexterity. So when I when I create a word cloud about the work that we've been doing, I get this sort of image, and obviously you can see robots are at the very center of it, but there's a lot to do about medical applications, so surgery, breast examination, diagnostics, a lot about teleoperation, haptics, interfaces, a lot about hands. So hands is kind of a common theme that I have, and I like to use these two images. This is what we call homunculi. On the left, you have the motor homunculus, and on the right, you've got the sensory homunculus. So basically, this has to do with the parts of our body that we use more for our motor functions or our sensory functions. And the more we use them, the bigger they appear. So you can see, for example, in the motor one, our mouth and our hands are the biggest part, and our head as well. And the sensory, of course, we have the hands yet again, the tongue, the lips. And obviously, what I like to keep from this is that for both the motor functions, which is what we use to take action, and the sensory functions, which is what we use to understand and interact with our environment, the hand is the common part here. And of course, if you look at the history, we have found connections between our hands and the fin rays of fish, which gives us some look into perhaps the fact that we were not always land creatures, but we have some sort of aquatic past. And of course, even a bit more recently than when we were perhaps having connection to being fishes, we were using our hands to build and to use tools to fight each other. So obviously, I'm not going to be staying so much on the fighting. I'm going to be staying more on the use of our hands, since when we are kids, we learn this is the first thing that we usually use to interact with the environment. We use them every day to cook, to play, to touch each other and feel close to people, especially during lockdown. I think that probably will mean a lot to a lot of us. And of course, on the bottom left, you see one of the applications of my work, which is surgery. And in fact, I'd like to start from this. So when I'm talking again about anthropomorphism in surgery, of course, I don't mean, two human-like robots talking to each other or actually doing a surgery on their own automatically. We are not there yet. We are not at that point. And I don't even know if we would want to go there exactly. We use robots to assist us. It's robot-assisted surgery. So you might have heard of this system. It's called Da Vinci, and it basically has separated the patient bed and the robot to the surgeon's console. The surgeon is using these interfaces, these sort of joysticks that you can see now in the video, and these joysticks are controlling the surgical instruments that are on the bedside of the patient. So the point, though, about these instruments is that they are not very dexterous. They are usually looking a bit like chopsticks. And so we thought, what can we do to improve the whole system? What can we do to have some more natural teleoperation manipulation, to make it more dexterous, to make it also portable? We don't need the surgeon to be sitting on the console, not moving at all times. We want them to be moving, to be relaxed, so that they can be the most efficient selves that they can be. We want whatever interface we make to be adjustable, to fit their hands. And we also want the capability that the surgeons feel what they're touching, because now this Da Vinci system that I showed you in the previous video is teleoperated, and therefore the surgeon doesn't exactly feel what they're touching inside the patient's abdomen. So a few years ago, during my PhD, and then later in a bigger European project called Smart Search, I built this system where we had these anthropomorphic human-like fingers that you can see on the right video and on the left picture here. So they behave in a way that our hands do. They have many degrees of freedom, and which actually for the instrument is 13 degrees of freedom in total. And they are then controlled by one of the exoskeletons that I have made, and one of them you can see in the middle of the screen, which has 19 sensors in total, and basically measures the angle of your hand as you're using it. So basically it transfers exactly what your motions on your fingers are to the surgical instruments. So as part of this project, I made a series of different exoskeletons. You saw one in the previous slide. There are 3 different ones here. You see the blue one on the top left, and a hybrid ones on the top right and bottom right, where we used both rigid and soft materials. And of course, there we have been using magnetic sensors, and we have been using inertial measurement units as well, to try to make it as compact and as comfortable as possible. Something that we are continuing to work on now, not necessarily related to surgery, but we are applying it in stroke rehabilitation. We're also applying it in nuclear robotics and industry, by looking at work in glove boxes and glove box operators. At the bottom left here, you can see some of the work we'll be doing in haptic feedback. So these exoskeletons are mainly sensory, so they basically can track what your fingers and hands are doing, but they can also, through a cable system, a cable-driven mechanism, give feedback back to you. So you're let's say you're grasping something in a teleoperated way, you're squeezing it too much, therefore the exoskeleton will take action and give you some resistance to feel that you shouldn't be putting so much force there. So moving a little bit more into the haptics here, you see some little device which we call fingertip haptic device we created with one of my students a few years ago. Whereas we were interested in applying some sort of force feedback or small forces, so almost tactile feedback on the fingertip of a surgeon or of a doctor who were trying to diagnose something in a teleoperated way. So we created this device that you can see in the video, which basically has a little inflatable soft pillow made out of silicone, which can inflate and deflate, therefore changing the stiffness, and therefore also being able to move up and down with a linear actuator and squeezing your fingertip. So using these 2 features now, we were able to create an array of different sensations, and then we were applying that using a virtual environment experiment where the users who were either doctors, clinicians, or non-clinicians, to try to distinguish between areas of stiffness. We had smaller, softer, and more rigid ones. So therefore, if we can apply this further into other applications of surgery, detecting any cancerous lumps, but of course also about manipulation of objects, this can have really crucial and big impact into in-hand manipulation and improving this dexterity. So moving on from that, this is now a project called Artemis. It's a partnership between Imperial College London, University of Bristol, and the University of Lincoln, and it's funded by Cancer Research UK. It is aimed at creating a system and a platform for an automated breast examination system. I'll play the video, which will show you a little bit the concept behind it. So we're aiming at increasing accessibility. So here you can see the user having booked a slot or an appointment, can go into the private booth and without the help of a clinician, have a regular breast examination. And this can be every 6 months or as frequently as needed. So here you can see a close-up of one of our designs. Here you can see what we call the lotus flower. This white part is, let's say, the fingers. They are soft, they're flexible, they are safe, they're compliant. They will not hurt the skin that they come into contact with. And the other part here that you might see here is a little bit of a black, hemisphere. This is also made out of silicone, and it is actually a smart sensor. And I'll show you more about this in the next slide. This is actually work that we've been doing with a couple of students, one of which is George, who is chairing the session. So the important part about this is that young women do not actually get the screening that they need, especially in the UK. NHS is sending screening opportunities to women usually above 50 years old. And therefore, by having an automated system like this, we're hoping to increase accessibility. So in this slide here, you can see one of the smart and soft sensors that we are exploring. This is the work that they've been doing with George Jenkinson and of course, Andrew Kahn. So you can see here that there's a soft silicone again, which has attached tubes to it, basically works in a pneumatic way. And you can see at the top right, as it is basically exploring a fake soft silicone that is there to emulate skin. In the middle here, you can see what I think is really interesting, that even with this little sensor, which is a fingertip in diameter big, you can detect features that are as small as 0.6 millimeter thickness. And I think this is really pushing the state of the art, especially since what we're really aiming here is not just to look at not at surface sensing, but looking more in depth and trying to detect lumps or abnormalities in a 3D volume. And we're doing that by basically, again, changing the stiffness by inflating or deflating the sensor to increase the range. And this one is a similar concept sensor, but this time it includes different technologies. It has a camera inside, which is basically looking at the deformation of these pins that are on the inside of this membrane. And at the same time, we are again employing pneumatic actuation here. As this is basically running, you can see how the internal pressure is changing, and how then we can track the position and orientation of the pins inside the membrane. So this is work that is actually being published tomorrow. So it's very fresh, and I hope that we will share more of this as time comes. So I mentioned before the lotus flower I showed you in the concept video of Artemis. This is bio-inspired, and it has come a long way from a simulation in software framework that you can see here on the left. Now on the right, we have actually manufactured it, and we are actually acting it with a cable-driven mechanism. And you can see here it has a dummy sensor. This white rigid part is basically where the soft sensor that I showed before will go, and the rest of the mechanism here, the rest of the device is again soft and rubbery and safe to touch. So moving on to one of my other projects with my other researchers, we have been looking at how we can use our expertise on hand tracking, on assisted living, as well as rehabilitation. So especially for stroke rehabilitation here, we have been looking at creating exoskeletons that are soft again, work either pneumatically or again in a cable-driven way. And here you can see the work of one of my students, where he was able to move passively the fingers of a hand by using the system here. With the back here, you can see that you've got an array of motors and a cable-driven mechanism. So the point of this is to be able to extend the range of motion when you as a stroke patient cannot actually move your own hand, but also to help with activities of daily life, such as grasping a bottle, moving a cup of tea, and so on. So I'm going to jump to one of the last slides now. So this is one of my projects that I'm very, very passionate about. It's about sign language learning and how we can use robotics to facilitate that, to make it more interesting, more engaging, and to make it something that people want to do. And this is not about creating yet another glove that reads sign language, but it is more about interacting with people who do not usually use sign language, who perhaps are hearing people and therefore do not feel that they have the need to do so. But it's very interesting in the deaf community. And if you look at the French deafhood principles, there is a suggestion that if we cannot sign, we are unable to use all our senses. Therefore, we are sign impaired. And I find this really, really interesting as a concept. And of course, I'm always very interested in hands and how we can use them to extend our senses and interact with our environment. And I think another point is that often there are things that we cannot actually communicate with using just speech, but sign language can actually be more powerful at these points. So moving on to space robotics, this is a project that we started a little bit less than a year ago, about 9 months ago, and it is in collaboration with Teleoperation Space, UK, and it is also funded by EPSRC via an iCase. And it's about exploring space technologies and how robotics can help in the case of manipulation, teleoperation. So we're exploring haptics and trustworthiness in the presence of a signal delay. So when you are on Earth and you are teleoperating something that is in orbit or the space station, or if you are in orbit of Mars, for example, and you're trying to teleoperate a robot that is on the surface of Mars. So obviously you can see that we have quite a loop here that depends a lot on the hardware. It depends a lot on the vision of the astronaut, but also it depends on the signal delay. And by using haptics, we're hoping to mitigate some of the problems that we have in this teleoperations use case. So this is, I think, the end of my talk. I ran through a few of our projects, but definitely not all of them. And of course, lots of this work is not mine exactly. It's I'm supervising and guiding a lot of my researchers, which you can see here. And I first and foremost will thank them for the amazing work that they do. I will be open to any questions that you might have. Thank you for attending.
Great, thanks for that. It's as you say, I'm obviously familiar with your work, being well, as I'm being shown, my picture's being shown there, so I'm clearly part of your group. But it's nice to hear a overarching narrative, one that I often hear from the inside, as it were. So there's quite a lot of projects going on. You just presented there, so it's clear what the academic route of everything is. I was wondering what ways do you see this, as one of the purposes of this conference? So what ways do you see that you might be able to potentially collaborate with people in industry, or in what ways are you already?
Oh yeah, thanks. I hear my voice now.
Oh,
Sorry. Yeah, that's a great question, actually. Thanks for it. It's a good opportunity to elaborate on that. So, as I said, I'm collaborating with Thales Alenia Space for my space robotics and haptics project. And this is through an iCase. So basically, EPSRC and the company are co-funding a student researcher to work for 4 years in between the University of Bristol and the company. Other ways, of course, to work. I mean, I mentioned nuclear robotics. So this is part of NCNR, which is National Center of Nuclear Robotics. So we do a little bit of work there, and we're looking at glove boxes. But I think that it really depends on the company, and I'm really looking for collaborators, especially in the medical applications, because as I showed, Artemis project is now coming to an end in December, and we're going to be looking at moving forward with the bigger project and trying to take our research outcomes and make them a little bit more translational. So if companies are interested in that sort of area of healthcare. But as I said also before, a lot of my expertise in exoskeletons, soft sensing, have application in many different fields. So it's the same sort of concept if you look at it closely. If you look at surgical robotics, that we're just using little tiny instruments to do little tiny operations, it's very, very similar. If you go to nuclear robotics, underwater robotics, oil industry and space, they again have an operator who is trying to do some really fine work in a remote location. And I find that the concept of a hand exoskeleton or a hand tracking device is something that we are lacking a little bit. Commercially, we have a lot of soft or semi-soft hand tracking systems, but they usually give you an average of the curvature of your finger. They do not give you detailed angle information, which is really what we have been aiming for all the past few years now. And this is why the exoskeletons that we've been making have 13 degrees of freedom in the fingers plus 2 in the wrist, so 15 degrees of freedom in total. Sorry, you have to unmute yourself, George. Sorry,
I forgot about the echo. So we have a question that's come in through the YouTube live channel from a GM, who's asking, they are curious if you've entertained using a haptic providing robot in conjunction with VR environments. So I suppose that would be, using the two together, wearing a Oculus Rift or something and having a haptic feedback.
Yeah, that's a great question. It gives me the opportunity to talk about maybe a couple of other projects really quickly. So in the surgical domain, we actually created a virtual environment, a virtual reality environment, where we had the simple task. Well, this is not very simple. The task of tying a suture, basically tying a surgical knot, and then we were using the haptic arm, the haptic robotic arm, and the surgeon were holding that. So different surgeons were holding a haptic arm to try to then tie the knot, and we were testing how haptic feedback can actually help them break the thread or not break the thread, because the assumption there was, or not really the assumption, the truth is that when surgeons start to train, they usually break the thread really, really quickly or break the skin even. And another project that I did show a little bit about was when we had a virtual environment, which wasn't at the time reality. There was a virtual reality. It wasn't with Oculus at all, but it was similar, and we could have done it in that style. It was about trying to locate where the tumor is and if there is one. And we did it again, not with a haptic arm at that point, but with a fingertip haptic device that we had developed.
Okay, I mean they sound like interesting projects too. I had one thought. I suppose when you started your research and settled on doing a glove, I was wondering whether, because I often see publications about people who have advanced video technologies that can track, SLAM for example, can track where people are very precisely. But I would suppose it has some use in tracking people, or could have some use in tracking people's hands. I can imagine some problems to do with occlusion. You can't track people's fingers that are out of sight particularly well. But is that something that you trialed or thought about and eliminated as not being good enough? Or
Yeah, no, this is a good observation actually, especially when we're talking about hand tracking devices that include vision or optics. That is something that happens a lot. But we have completely basically chosen not to use these technologies, and instead we are using hardware. We're using specifically magnetic sensors and IMUs, and we don't have any occlusion for them. We have actually a very good sub-degree accuracy, even in some cases. The only challenge that we have is that to make sure the hardware fits well on the hand, but we are now mitigating that by using a combination of rigid and soft materials. And therefore, when you use something like silicone, let's say, that really nicely embraces the hand and stays in place. So therefore, we don't have much to worry about there.
Well, that sounds like a good solution. We've still got a couple more minutes for questions, so I'll crack on. So I was wondering if you could perhaps tell us a bit more about the connection between your sign language project. I like the idea that people who can't sign are I can't remember what the phrase was, sign impaired, I think you said. I quite like that as a way of thinking about it. So where does this stem from, and how did you start that work, and how does it connect with the rest of it?
Well, I suppose it might be obvious that it has to do again with hands and involving that. And I really agree with a lot of philosophers that say that without our hands the way they are now, we wouldn't have progressed through the primeval age of humanity. We would still probably trying to do something else in caves without the dexterity that we have now. So this interest I have in hands kind of led me to sign language, and I find it really fascinating. But of course, this also connects to how I feel very strongly about having diversity and inclusivity in our environments. And I looked around and I didn't see any of the deaf community surrounding me. And I thought that if we don't have them, what else do we not have? And obviously, this means that we don't have all the voices we need. And I think this is really important in any field, but especially in engineering, as we are really impacting society by our devices, our decisions. And therefore, and then Artemis project we were doing with the breast, automated breast examination system. One of our goals is to increase accessibility to population that sometimes do not go for screening or do not have access to screening. So all of this ties together, and I really hope that by pushing through this sign language learning project, and I would definitely invite companies to contact me and interact and see how we can actually push this forward or try different technologies towards that aim. I think that we can make a huge impact into introducing something like that into the UK curriculum, for example, that we can be teaching this in school. And why not, wouldn't we?
Yeah, so I think that's a good, I guess, a good broad point to make, that we have this idea that, or at least I have this idea that, technology and robotics and engineering should be a sort of great equalizer and work for everyone. So we need to, at a time as it appears now in our field where it's sort of really becoming ubiquitous, we need to work hard that it does actually do that and not leave, for example, deaf and signing people behind. Okay, well, that brings us on quite nicely to the end of the time. So thank you very much.
Thank you.
For your talk. Cheers. And so next up, we have Professor Kirsten Eder, who is a professor of computer science and leads the Trustworthy Systems Laboratory at the University of Bristol, as well as the verification and validation for safety in robotics. research theme at the Bristol Robotics Lab. And her research is focused on specification, verification, and analysis techniques to verify or explore a system's behavior in terms of functional correctness, safety, performance, and energy efficiency. She holds a PhD in computational logic, an MSc in artificial intelligence, and a Master's of Engineering in informatics. And in 2007, she was awarded the Royal Academy of Engineering Excellence in Engineering Prize. So I'll now hand over to the esteemed Kirsten Eder, who is ready with her presentation. You're ready.
Okay, thanks very much. Hello, everyone, and welcome. Today, I want to focus on our recent research on autonomous systems with a flavor of the trustworthy systems and verification and validation angle. Okay, so in the Trustworthy Systems Lab, we take the view that, well, trust first needs to be gained, can easily be lost, and is hard to regain, that then can be lost again. However, trustworthiness should be demonstrable. So our research is focused on developing techniques that can be used to gain confidence in the correctness of a system with respect to its specification, in the security of a system, and also in the trustworthiness of a system. Now, confidence in a system's trustworthiness can be gained in a variety of different ways, including by design, through transparency, but also through rigorous verification and validation. And in this presentation, I would like to walk through each one of these in turn. But before I do this, I would like to focus on terminology for a moment. Now, my background is in hardware design verification. Bristol has a very vibrant microelectronics design industry, and for them it's really important that when they send the chips to manufacture, they know that the designs are correct. So they put a lot of emphasis onto verification. Now, in the hardware community, verification is understood to be the process used to gain confidence in the correctness of a design with respect to its specification. And what's important about this is there is no particular technique that is mentioned in this definition. And indeed, they use quite a variety of techniques. They use simulation, they use formal verification, and they use lots and lots of combinations of these in order to make sure they gain the confidence to send their designs for manufacture in a timely manner. Now, my experience is when I talk to someone from the software community, when I say verification, what they hear is formal verification. Okay, and just to point to the standards, according to the standards, as you can see here, verification and validation techniques do include formal methods as well as test and simulation-based techniques. Right? So verification and validation does not exclusively mean formal methods. It's clear that testing and simulation are also under that heading. So when I say verification, I mean the process used to gain confidence. And we use any technique that helps us gain confidence. Okay, so let's start. I said that confidence in a system's trustworthiness can be gained in many different ways, including by design. And that means systems that are simple by design can typically be understood, and if we understand something, we might trust it. Now, therefore, simplicity and clarity of both the design and implementation are two of our key research objectives. We have recently started a new research project that asks the question, what makes a system trustworthy? From the perspective of the end user, but also considering regulatory requirements and ethical aspects. Now, it's all too easy to make things work without considering how one can demonstrate that it will always work safely, securely, and is reliable. Now, this requires a change of mind and a change of design process. In fact, engineering has matured so much now that we are capable of building a variety of complex autonomous systems and robots. And I claim the intellectual challenge now is to build them in such a way that their trustworthiness or correctness with respect to the specification can be demonstrated. And so promoting trustworthiness to a first-class system design objective is an area that we are focusing on in the Trustworthy Systems Lab. Now, the second way of gaining confidence in the trustworthiness of a system that I mentioned was through transparency. So systems that allow us an insight into how they make decisions, why they act in a certain way, and potentially also how they use resources such as power, energy, and time. Again, these systems may become understandable, and through that understanding, we might trust them. So transparency is another one of our key research objectives. Now, there is a lot of research on transparency in terms of the decision-making of autonomous systems, but I'd like to illustrate the principle of transparency in a slightly different way today. I would like to focus on what I'm calling energy transparency, and I mean by this the energy consumed by a computation. Now, I'm interested in this area because from a verification perspective, I typically focus on safety and functionality, but from an end-user perspective, if a system runs out of battery prematurely, I consider it as faulty as if it had a design flaw. Which is what brought me to the area of energy transparency, or at least energy modeling, and that then leads to the concept of energy transparency. Now let me explain. What we see here at the bottom are 4 heat maps. They show the energy consumed by instructions as data is processed in a CPU. From left to right, we see addition, subtraction, shift left, and a logic AND operation. Now, while the logic AND might perhaps be the most beautiful, and indeed we won an art competition with this heat map, the subtraction heat map, which is the second from the left, the half blue and half red, is perhaps the most interesting if we want to better understand how energy can be saved during a computation. So let's focus on that. So what we see here is this subtraction operation applied to 8-bit data. On the y-axis, we've got operand 1, from which we subtract operand 2. So let's pick a value, 160. And you can see as long as we're taking values which are less than 160, we end up using little energy. As soon as we get to the diagonal and we get a negative result, we get much higher energy. Now, for the computer scientists amongst us, this is the consequence of using 2's complement representation inside the computer, and that gives us a leading set of 1s. So when we switch from positive numbers to negative numbers, there's a lot of bit switching, and bit switching costs energy. Now, this is very, very fine grain, right? But in principle, in our research, we capture energy consumption of computation in energy models. And that gets me back into the autonomous systems area, because such models can be used in order to analyze and predict the energy consumed during a computation, ideally at compile time or alternatively at runtime, without the need to measure explicitly. And in the European-funded project TeamPlay, we did exactly this. We were modeling energy consumption, but also time, as well as security. And we then enabled the non-functional properties to be analyzed effectively and treated as first-class citizens during system development and at runtime. We started off with software contracts, and these software contracts then flow into the source code. We then have our energy models, which support the compilation and sophisticated analysis for optimization. And then we applied this to a number of use cases, most of which you will find at the BRL. These include drones, smart Internet of Things devices such as parking lot meters, a camera pill, which is a really interesting application because you really want to make sure it's as small as it needs to be in order to take pictures inside you, and it uses the energy that it needs economically. And then also a number of space applications. Now, finally, let me get to gaining confidence in a system's trustworthiness or correctness through verification and validation. So in our research, we investigate how to complement rigorous proof with simulation-based testing. I'd like to illustrate this here on a small example from control theory, so a very small controller. So at the top here, you see a control system, and the question really is whether that system is correct in terms of what the designer tried to achieve and what the specification actually required it to do. Now, in order to establish the correctness of this system, you'd have to think about how to capture the requirements in a formal way and then to check these requirements. Now, what you can do is you can capture the inherent control law in a set of assertions. So we are going back here to the requirement of stability of the system, and we're using control theory based on Lyapunov, and that gives rise to what I've previously in the previous slide shown here at the bottom, a set of assertions that capture stability requirements of this system. Now, with this set of assertions, we can now go and see how we can verify them. And indeed, there are two different types of assertions that we have captured here. One can be tested in simulation because there are no variables involved. So we can do this using Simulink in this case. Or alternatively, what we can do is we can formalize and translate our Simulink diagram into a formal logic, so first order logic in this case, and then use automatic provers in order to establish the correctness of those properties which actually include variables, right? And so there are automatic theorem proving techniques available which can be used in order to capture the control laws and then automatically prove the properties based on a theory that the theorem prover uses for the proof. So a particular challenge in this area is, of course, capturing the logics that underpin control theory in such a way that the automatic theorem prover can take full advantage of this, which is one of the research challenges. But in principle, what I'm saying is rigorous verification and validation doesn't necessarily just mean one technique. You really need to think about what it is you want to verify and then find the most suitable technique in order to achieve your goals. So if you've got a problem like this, we'd be pleased to hear from you. Now, let me finish with some challenges for verification and validation of autonomous systems. The biggest challenge is perhaps the specification challenge. Specification is absolutely essential to perform verification and validation. If you think about the system design process, we typically start from a specification, we capture the requirements, and then we go systematically in steps of refinement through the design process all the way down to the eventual implementation. And in this process, we also split the system into different components, which we then compose together again. Now, the starting point, both for the verification as well as for the design activity, is the specification. And so it's really critically important that we develop techniques to specify the behavior of autonomous systems. And that is a research challenge that we are investigating as part of a new EPSRC project, which is focused on trustworthy autonomous systems with evolving functionality. Now, typically, specifications, we know how to write them and we know how to do them. But for systems with evolving functionality and for autonomous systems, it has turned out to be quite difficult to capture what they should be doing in a specification, which is why I list specification as perhaps the most important challenge for autonomous systems from my perspective, because without a solid specification, it becomes very, very difficult, if not impossible, to do verification and validation. The next big challenge is automation. I think we need a lot more automation in the verification of autonomous systems. And some of the research we are conducting at the BRL, in particular the Trustworthy Systems Lab, is focused on simulation-based verification and the automation, in particular, of the test generation process. And the final point that I've got listed here is on innovation. Now, innovation is critically important for science in general, but I think we need to be much more creative when it comes to the verification of autonomous systems. We need to think about how we can creatively combine techniques, and most importantly, we need to be more clever in harnessing the power of artificial intelligence for verification and validation. So in the Trustworthy Systems Lab, we have introduced a new technique, which is called agency-directed test generation. Now, agency-directed test generation uses the power of artificial agents in order to generate test stimulus. And we apply this to human-robot interaction and also to the verification or simulation-based verification of autonomous vehicles. Now, a particular challenge with these applications is that the system under test is a responder. It responds to its environment. And if the system is truly autonomous, it's going to be impossible to enlist all options that the system has in order to respond to a given test. So our standard way of testing, namely prescribing a test and then having an expected response, won't work so well on these systems. And for this reason, we are harnessing multi-agent systems. And these multi-agent systems effectively are active agents in a test environment. So what you can see here is a gym environment with a bus stop. So the large vehicle is effectively a bus. And the red vehicle is the autonomous vehicle. And any of the other vehicles, the black ones, are intelligent agents. So they are artificial agents which have certain objectives, certain goals. And in an interesting test situation, we would train them to make it rather difficult for the autonomous vehicle. And we would watch out to see whether the autonomous vehicle actually gets into a situation where it has to make tricky decisions or potentially even violate the rules of the road, or maybe only social conventions on driving and endangering other drivers. So we need to be effectively more clever in harnessing AI for verification, and at the BRL in the Trustworthy Systems Lab, we're doing that. So if you want to get involved in this and try this out, it's all on GitHub, and the associated publication you can find there as well. Okay, so these are all the researchers in the Trustworthy System Lab. There is my email address, and I'd like to thank you for your attention, and I'm waiting for your questions.
Thanks very much for that presentation. That was very interesting. Yeah, so the questions are open for anybody watching. In the meantime, I suppose, because there's a big application of this at the moment. It's probably looking into autonomous cars, as you showed a short example of at the end, where you had a single autonomous car and then a few agents that you said whose purpose was essentially to make it difficult for the autonomous car. Does this change when there are, how does this scale is really what I'm getting at. Is there a sort of critical mass at which there are autonomous cars and they can all verify each other, or does it not make that much difference if you have one autonomous amongst 10 agents?
At the moment, so it's a really interesting question. At the moment, we're interested in particular autonomous cars and their driving behavior. But you can envision a future where you can train vehicles in an environment like this, and then you would have multiple vehicles, and it'd be interesting to see how they learn from each other. But at the moment, our research is focused primarily on on individual vehicles.
Oh, yeah. Okay. I imagine that's working with the available autonomous car. So is the process of it that you write the policy that the autonomous cars behave by, and they then go on to train themselves, or do outside companies come in with a certain set of things and say, we'd like you to verify this?
Well, we could essentially do both, but the environment that we have allows us to integrate external driving AI. So that might be third party, like we have done with several CAV projects, where we integrate the AI that our project partner has developed into a test bench, and then we control the vehicle surrounding the vehicle under test. There is also open driving AI that you can we could integrate, and we've also got a few controllers ourselves. So the main focus of our research is really in the development of the test environment, as well as in automating this test environment or automating the process of testing, and then finding tests that that challenge the vehicle or the autonomous vehicles, if you want, and to monitor and watch and to flag up any violations of rules as the simulation is exercising.
Yeah. Okay. I can get on board with that as a process. All right. So I think with that, I'll begin to thank all of our speakers for everyone's contribution today. I don't know if Antonio, you want to come back in to say a closing comment for this thread.
Yeah, sure. I just also would like to thank everyone, and like Kirsten, who was the last speaker, and who we also collaborate on some of the space robotics and trustworthiness. So yeah, thanks very much, and thank you, George, for chairing the session, and all the audience for sticking with us and following us to the end. I think next we have the closing at exactly in 6 minutes by Professor Arthur Richards and Professor Manuel Giuliani. And the theme of that will be how to engage with us further, and then there might be some more one-to-one sessions at the end. Okay, then. So then I'll say good afternoon to everybody, and hopefully see you in person sometime at the BRL.